Alright, so in this video I'm going to run through a bunch of solving moles to moles limiting reactants problems. So what you have to realize is that we're going to be faced with a situation where we have multiple reactants forming one or more products. And what we have to do is we've got to identify the limiting reactant. And one of the properties of the limiting reactant is that it is the reactant that gives the smallest yield. So what I'm going to be given is the amount of one substance, and I'm going to turn that into the yield of one of the products, and then I'm going to be given the amount of another substance, and I'm also going to turn that into the yield of the same product. And then I will have two numbers, and the smallest of those numbers will be the theoretical yield, and that will also allow me to identify what is the limiting reactant. So the types of calculations that I'm going to be doing in these problems are what we call moles to moles problems. So I'm going to be going from moles of a reactant to moles of a product, and I'm going to be doing that twice in order to identify the limiting reactant. And if you recall, in order to convert from moles of substance A to moles of substance, in this case we can call it C if we wanted to, but we normally call it A and B, we're going to multiply by the appropriate mole ratio. So in order to get a mole ratio, you have to have a balanced equation, otherwise your mole ratio won't be correct. So in each case, we're going to be taking a certain number of moles of reactant, multiplying that by a mole ratio, and getting a moles of a product. And we're going to do that at least twice in order to identify our limiting reactant. So what we've got to do is get a balanced equation. Now, there are a couple of ways of getting a balanced equation. You can, if you want, even look up online equation balances that will help you figure this out. So keep that in mind. So it says nitrogen dioxide, gas, and liquid water react. So there are two reactants, NO2 gas and liquid water. And they're going to react to form nitric acid, HNO3, as an aqueous solution. And in addition, we're also going to get nitrogen monoxide, which is a gas. So now we've just got to balance everything. So I'm going to begin with nitrogen, and you can see you've got one nitrogen on the left, but you've got two on the right. So I'm going to put a 2 there, and at least preliminarily, those guys balance. Now I'm going to move on to oxygen, and you can see I've got 2 times 2, that's 4, plus another one, I've got 5 on the left, and then I've got 3 plus 4, plus 1 gives me 4 on the right. So how am I going to get this all to work out? Well, let's think a little more here. I've got some hydrogens over here. I've got 2 on the left, and I've also only got 1 on the right. So I've got an imbalance with my oxygens and my hydrogens. So what might I do here? Well, how about if I just bring that guy up to 2, and now they balance, but of course now the problem is that I've got 3 nitrogens on the right hand side. So what about if I made that a 3? Okay, so now they balance, they're back in balance. So at this point I've got nitrogen and hydrogen to balance, but what about my oxygen? Where's my oxygen at now? So I've got 3 times 2, that's 6, plus another 1, that is 7. And then on the right hand side I've got 2 times 3, that's 6, plus 1, that is also 7. So by some miracle that all balances. So now I have a balanced equation, which means I can now get correct mole ratios. So then it says, suppose you have 5 moles of NO2. So I've got 5 mole of that guy and 9 mole of water. 9 mole of that one. Okay, everything looks like it's going to be 2 sig figs, by the way. So then it says, suppose as much as possible of the NO2 reacts, how much will be left? So let's see, what we're really asking is this. We're asking what reactant gets used up first. Now, if NO2 is the limiting reactant, then there'll be 0 moles left. But if water is the limiting reactant, there'll be more than 0 moles of NO left. So we've got to figure out what's the case, right? What's the case? What is the limiting reactant here? So how I'm going to do that is turn each of these guys into a product, into moles of product, and see what we get. So I'm just going to pick, it has to be the same product. So what I see is I've got 5 mole of NO2, and if all of that was used up, I would make 2 mole of HNO3 for every 3 mole of NO2. So you see, I'm just going to multiply that by that. And then you see in that way, boom. So 5 times 2/3 is going to be obviously less than 5. It's going to end up being 3.3 mole of HNO3. So I still don't know whether NO2 is my limiting reactant or not. I've got to do the same type of calculation, but for the H2O. So now I've got 9 mole of H2O, and I've got to multiply that by the mole ratio, and I get 2 mole of HNO3 for every 1 mole of H2O. So what have we got now? Well, we just got to that by that, so I would get 18 mole of HNO3. So what's smaller, 3.3 or 18? 3.3 is smaller. So what that's telling me is that NO2 is my limiting reactant. And so what's going to happen is the NO2 and the water will react. 1 mole of NO2 will get consumed. 2 moles of NO2 will get consumed. 3 moles of NO2 will get consumed. 4 moles of NO2 will get consumed. 5 moles of NO2 will get consumed. And then the reaction will stop because we've run out of NO2. Now there will be some water left over. We can't use up all of the water. So what's going to happen? How much NO2 is going to be left behind? None. There's not going to be any because it's the limiting reactant, so it gets completely consumed. So the answer to this one is 0.0 mole of NO2 remains. There we go. So that's that. So let's move on and do another one. So whenever we identify the reactant of interest as being the limiting reactant, that tells us that that's going to get 100% used up. So if you were making sandwiches, say you were making cheese sandwiches, if you had 10 slices of cheese and 25 slices of bread, and every sandwich required 1 slice of cheese and 1 slice of bread, you know that what's going to happen is you're going to keep making sandwiches, and at the end you will have no cheese left over and some bread. So that's what's going on there, right? So let's have a look at this one. Solid aluminum and chlorine gas react. So Al solid plus Cl2 gas to form aluminum chloride, AlCl3, and that's a solid. So what I see here is that it doesn't balance, and so I need 2 of those and 3 of those, and then I'm going to need 2 of those, and now everything balances, right? And you can check that 2 moles of, let's just do it this way. Aluminum, we got 2 on the left, 2 on the right, and then chlorine, 6 on the left, 6 on the right. Okay, so now we're ready to go on and identify what is my limiting reactant. So how much do I have? I've got 13 moles of aluminum, and I've got 1 mole of CO2. So let's do the math. We've only got one product, so I'm going to turn all of that into AlCl3, and I'm going to turn all of that into AlCl3. So let's just do it. So we've got 13 mole of aluminum and multiplied by my mole ratio, 2 mole of AlCl3 for every 2 mole of aluminum. So you guessed it, if all of my aluminum reacted, I could make 13 mole of AlCO3 if it could all react. Now it might not be possible for it to all react if it's not the if it's not the limiting reactant, right? It might be the excess reactant. Okay, now we're going to do the same for the Cl2. So I've got 1 mole of Cl2 times 2 mole of AlCl3, just from the 2 there, per 3 mole of Cl2. And so that cancels. And what am I left with? 10 times 2 on 3. So that's going to be 6.67 moles of AlCl3. 10 times 2/3, right? 6.67 mole of AlCl3. So what that means is that Cl2 is the limiting reactant and none remains at end of reaction. The question is how much aluminum remains though, right? So for the limiting reactant, everything gets used up. So how much of the aluminum got used up, because that is that. What is the limit? Oh, we're actually done. It just says what would be the limiting reactant. So we got it. We figured out the limiting reactant. It is Cl2. All right. That was easy. Solving moles to moles, a limiting reactant problem. Methane and oxygen react. CH4, it's a gas. O2, it's also a gas. Just going to cut to the chase here. There's the balanced equation, okay? I'm able to do this very quick because I've been doing it for a really long time. Just double checking everything. Looks good. Yep. Okay, so everything balances, like 1 carbon, 1 carbon. 4 hydrogens, 2 times 2, 4 hydrogens. 2 times 2, 4 oxygens. 2 oxygens plus 2 times 1 oxygen, 4 oxygens. So everything is good. There we are, nice and balanced. Can't do anything until we're balanced because we need that mole ratio. Okay, here we go. 13 moles of that guy. Oh, hang on. Yeah, 13 mole of that one and 5 mole of that one. Sometimes you kind of rush these and you can get ahead of yourself. Suppose as much as possible of the CH4 reacts, how much will be left? First step, identify the limiting reactant. So I'm just going to turn it all into CO2 and see what we get. So 13 mole of CH4 times 1 mole of CO2 for every 1 mole of CH4, and you guessed it, we get 13 moles of CO2 if all of my methane reacts. Then we've got 5 mole of O2 multiplied by, we get 1 mole of CO2 for every 2 mole of O2, which means if all of the O2 reacts, we could form 2.5 mole of CO2. So what this means is that O2 is the limiting reactant. And that means that there is none left over. It also means that methane is what we call the excess reactant, and some is left over. So our job is to figure out how much is left over. So how we're going to do that is we're going to take the starting mole of methane, which was 13, and then we're going to subtract how much reacted. Alright? So what we've got to do is figure out how much methane is reacted. So 5 mole, the entire 5 mole of the O2 is going to react, and we have 1 mole of methane for every 2 mole of O2 in our balanced equation. So that means that 2.5 mole of methane reacts. Here we go. So if I started with 13 moles of methane and I use up 2.5 moles, that means that 10.5 mole of methane remains. Okay, so I think that makes sense to me. All right, so there we are. All right, so that's it. So it's all about the concept of the mole ratio and also the concept of the limiting